Sure. Hi guys, again. So I think what I should probably just start off with a bit of an explanation. If you are sitting here right now in the advanced section, you probably have most, if not all, the information you need to solve IMO geometries. The main issue is that you don't really know how to spot the applications, which is why I'm tending to focus a lot on applications and how to actually solve problems rather than hitting you guys with lots of theory. Because you can always just learn theory by going on Google and textbooks and so on and other sources. And if there is something that pops up that's interesting or that you don't know, I will try to explain it. But I'm going to focus mainly on applications. And I think the first application is going to be today's problem 5. I wasn't planning on doing this, but there was a solution in the test that was far simpler than the one that I worked out and far simpler than the one that was officially given. So I'm going to show you that. And the reason behind this is because I think a lot of you guys didn't try question 5 because you saw it was question 5 and you thought this is a geometry and it's very hard, so I'm not going to do it because I'll have a better chance of solving another question. When in fact, if you'd maybe put a little bit more time into it, you might have actually solved it and then got 7 marks. In fact, there was quite a few partials that could have been given as well, so we're just going to take a look at that. So the full question is that we have a triangle which is acute, and you have perpendicular here D. This is A. This is B. This is C. Then imagine you have the circumcircle comes that. And then you draw the circle that's tangent, centered at A, and tangent to BC at D. Intersects here at X, and intersects here at Y. And then the proof, or the question I guess, is to show that this angle here, CYD, is equal to DXB. The proof goes as follows. You draw that. Then you notice that this circle here, I should give it a name, I guess, gamma, is tangent to BC, so we use tan chord. This angle, double angle there, this double angle there. And then similarly on this side, we'll take this as a triple angle, and this is triple angle. And I'm going to remove that. We'll just look at that one for now, and then we'll just do the stuff later. And I think we should give them some names. So let's call this X, and let's call this Y, then this is X, and this is Y. Now, let's call this one alpha. Then because CYXB is a cyclic quad, we have XBC is 180 degrees minus AX of X. Sorry?
You said something like the cyclic quad.
Yeah, so YCBX is a cyclic quad because by construction.
Oh, yes.
Yeah, so they were defined to lie on the circumcircle. Oh, sorry. So since that's a cyclic quad, we do opposite angles are supplementary. So this is 180 degrees minus alpha minus X. And then we do in this triangle here, X 180 degrees minus alpha minus X plus this angle here must equal 180 degrees. Then, so 180 minus alpha plus what gives you 180? It's alpha. Alpha. Yeah. So that was a lot simpler than I originally thought it was, and a lot simpler than, I mean, I originally thought it was simpler than what their solution was, and then I got that, and I was like, wow, that's nice. So yeah, just a bit of a lesson to all of us that things can be more simple than they seem. So give things a try. Obviously, if you're sitting there for like an hour, maybe move on. But yeah. Okay, and the next thing I want to move on to is, not actually there, it's in the top, is a question I found the other day, which is one of the coolest questions I've ever seen in my life. And so I thought I would show you guys because it's cool. Right. So, it starts with a circle. And then we have the center O. Okay. And we have a chord, which is longer than the radius. Okay. There, AB. And we have a point S on the chord such that AS is equal to R. So, then we perpendicularly bisect SB to D and C. And then we draw DS to point E. Then the question was to prove that CES is an equilateral triangle, which seems kind of ridiculous, if I'm honest. I don't know. That just seems crazy. So let's go about proving that.
Can I just ask, is OA equal to AS?
Yes.
Is a radius?
Yeah, so that was by
radius
construction. Yeah, so we pick S so that AS is equal to OA, which is R. So, first things first, let's fill in from constructions what we know to be equal. So this is a perpendicular bisector. So we know that BC is equal to CS, and likewise BD is equal to DS. And I should probably make this better. Let's use squares for these ones. And do we know anything else immediately? No, okay, so now we'll look at angles. So let's look at this angle here. That is equal to this angle here by the similarity of the construction. And notice that in CDB, this angle here, I guess I should give it a name, let's say X. X is subtended by the chord CB, and X here is subtended by the chord CE, which means that CB is equal to CE. So that's the first step. So now we need to get that ES is equal to SC or vice versa, or some other way of showing that this thing's an equilateral triangle. And the way I did it is that, sorry? So we want to show that CES is an equilateral triangle.
Right.
So we need that ES is equal to CE, which will then be equal to CS, so all the sides are equal. Or alternatively, we can show that one of the sides is 60, or that angle equals that angle, or something. And the way
I follow what you just did where you made the
where I got these two equal.
Yeah.
Okay, so we have an angle here, which is subtended by a chord CB.
Yeah.
And we have the same angle here, which is subtended using these two lines from CE. Because the angles are equal, they're subtended by the same length chord.
Oh, okay.
So if in any, if I have a circle, do you know much trig? Have you done trig?
Yeah.
Trigonometry? Do you know the law of sines?
Yeah.
So sine A over A equals 1 over 2R. So if you look in a circle of the same radius, this is angle A, and this is length A, then the sine of this angle over this angle is always going to be constant. Over this side is going to be constant. So if I have some other angle here, which is also equal to A, then we know that the sine of this angle over this length is also going to be 1 over 2R, which means that length is supposed to be A as well. Cool. So that's how we get that these two lengths are the same.
You were moving it too fast.
Sorry, I'll try to slow down. way we're going to go about showing the next bit is we're going to extend CS to the point here, which I will call S prime. And we're going to look at the lines that are created on the circle. And also we're going to look at, I believe, EA. Okay. So let's just chase some more angles quickly. Let's call this Y because 90 minus X is too big. Then subtended by the chord AB, we have angle AEB, which is also Y. And then by the symmetry here, we have this as Y. And then from vertically opposite angles, we have this as Y, which means that EA is equal to AAS. So that is also R. Now we're starting to get some interesting stuff. And then finally, we look at the angle subtended by AS. And we want it to be the same as this, the angle subtended by AE. So the way we're going to do that is we're going to connect AC. And we look at the angle subtended. So we have AS. Yep.
Isn't that already enough because you have like A is the center of the circle of like EOS and therefore ECS is like 60 degrees? Isn't that enough?
Sorry, I don't follow how you get 60 degrees from that.
Because if you have two circles that like both cover each other's centers, then it's like 60 degrees. Isn't it?
Yeah, okay, so
And you have that, so aren't you already done?
They have the same radius.
so you're going to the circle centered at A and the circle centered at O with radius R intersecting at E and S, yes?
Yeah.
So that will give you,
Surely
yeah, that should give you the 60 degrees, I think.
Yeah.
It's not the same triangle.
But just to confirm, or maybe people who can't see so quickly, if you have a circle, and you have another circle centered here, and then you have another circle.
What's the circles going to be sides?
Yes, absolutely. So if you have, he's referring to this, if you have radius here, radius here, radius here. So you know that. Oh, so you, but yeah, so I don't see how you're quite following to get the ECS as a 60 because C is not.
No, but if you join the two intersection points and then you, if you join the 2 points of intersection of that circle.
Yeah, so that's
the-
E and S, yeah?
Yeah,
Okay. So then you'll have this other circle here, so it's going through O.
yeah, and you have EC equals to CS already, so that's like the isosceles.
Oh, so that's centered.
Well, is it not just?
Then I think he is right, but I'm trying to get the formal argument out of it. So, are you confident that explaining this like writing it down and explaining it to an I mode coordinator will get you the marks?
Yeah, because then you just, isn't it well known that if you have two circles like that, then
I don't think you're allowed to claim that. I think you have to do it as a lemma separately. Yeah. But I'm still struggling to see where you get this 60 is from. Which 60 are you going
So
on?
basically join the two intersection points and the angle it makes with the center is 120 degrees and so
Oh yes, okay. Yeah, I see what you mean. Yeah, okay. So that's fair. So you have these two circles equal size, then that gives you 120.
yeah.
And then subtended there will give you 60.
Wait.
Okay. Yeah, that's fair. Yeah. The way that I was going to continue was basically saying that these two are the same, these two are the same, which means that this is a kite. which means that these two angles equal, which means that these two lengths subtend the same angle, which means this is also r. And we know that the angle subtended by the radius is 30, which means the angle subtended by 30 plus 30 is 60, and then from there you would get the 60 degrees. Yeah.
Can you just repeat that slow?
Okay, yeah, definitely. So using his method, we get that using this sort of diagram, we get these two equilateral triangles, which means this is 60 degrees and this is 60 degrees.
Why do you say it's equilateral?
So they are two circles with equal radius, centered on each other.
It's equal radius.
Yeah.
Yeah, equal radius. So this length is r because it's the radius, this length is r because it's the radius, and this length is r
But
because
that
it's the
can't
equal
be the
radius.
radius because it's not going to the top, is it? Oh, okay, sorry.
Yeah,
I've
they're
got
from
it.
the
I've got it,
center.
yeah.
Yeah.
Agree.
Okay, and since all the radii are equal, we have it's an equilateral triangle, so that's 60. Similarly, that's 60.
Got it.
And since that's the center, you have this angle here is half the angle subtended there, which is 60 degrees. And then my way is that you have these two are equal, these two are equal. So you have that CSAE is a kite. And so ECA is equal to ECS. And so the chords EA and AS prime subtend the same angle. And we know that EA subtend, the radius subtends an angle of 30 degrees. So 30 degrees plus 30 degrees.
Even using that method, you still have to prove that S prime is on the circle.
What? Sorry?
The second circle that you prove, you still have to prove that S prime is on it.
S prime? I don't have an S prime.
It's there.
This is S.
No, down below it.
Oh, S prime. Yeah, so it is because it's subtended by the same.
Right, but if you were using that proof, you would still have to find that that line is R.
No, because he wasn't using S prime, he was using S.
Right, then I don't see how that works. That's not
So
on the surface.
actually, that's a good point.
It's
Yeah.
not on the. It's not on the big. It's not on the surface. It's on the center circle there. What's that point there?
Yeah,
A?
he's right.
Not on the one center there. Oh.
Yeah. So you would still have to prove that S prime, I think, is on the circle. But that's not the whole. That's not the slow step. The one thing I wanted to show was that the important information is that the radius subtends an angle of 30 degrees, which you guys should remember. It's quite useful sometimes. And then just the general angle and ratio chasing. It's quite useful.
Can you just tell the last one, what the 30 degrees, we repeat that?
So imagine you have a hexagon, regular hexagon that's subtended in a. It clearly fits in a circle because the distances here are all the same. Specifically, they are r, and we know these are all equilateral triangles, so we can just fill in all the r's everywhere. And we know that this is 60 degrees. So the angle subtended at the edge will be half of what's subtended at the center, which is 30 degrees. So we know the radius subtends an angle of 30 degrees. Yeah. Or a chord of length radius, I guess, if you're trying to be like the most accurate and very correct. I just thought that was a cool problem. So I guess just no, I've got half an hour. Right, I need to remember the percent. So final calculation is actually on my phone because I got it from one of the other previous IMO team members, and we're going to try to solve this one together because this was written by someone much closer to your age than my age. And And so the question is, we've got a circle, gamma, and a line called L. And specifically, L is not intersecting gamma, and we have to find the locus of all points. So I'll just write this down because I probably have to explain some terminology. P such that P is the center of a circle omega such that L is the radical axis of omega and gamma. Yes, okay. So I'm probably going to have to explain some terminology. So, who knows what a locus is? I guess who doesn't know what a locus is? Okay, I'm going to have to explain that. I explained radical axes yesterday, but I'm going to try to do a better job today. Well, use it at least. And I think the rest is probably self-explanatory. So, let's just talk about locuses for a second. So, a locus of points is the set of all points that satisfy a certain property. So, if you think of the locus of all the points that are circumcenters of any particular triangle is precisely one point, which is, so it's fixed. The radical axis is the locus of all points that have the same power with respect to two circles. So it's a way of defining sets of points, and they usually take some sort of shape, like a line or a conic, like an ellipse or a circle or a square sometimes. So we want to find all points, say P, where I can draw a circle around them, and then have every point on P has the same power with respect to gamma and omega. So the way to Oh, you're just stretching. Okay. So the way we're going to start with this. Well, actually, what do you think? How do you think we should start with this?
May I propose what I think the locus is?
Yeah, sure.
The perpendicular through O, where O is the center of the circle.
Okay, so so here's the center, and you say it's the like the infinity to infinity. Okay. Okay, so that's our first suggestion. What do we think of the suggestion? Yes?
Wouldn't there be circles where L would pass through gamma?
Precisely. Well, not necessarily, because we can make the radius as big or small as we want. But you have brought an interesting point. Consider a point here, right? So if this is in fact our locus, then a point here would be would have a circle such that is true. If we had a circle here, where would the radical axis be? It would be between, surely. So we know we can't have a point in between here and here. So we will, that nothing there is there. And yeah, also similarly on this.
Just make a circle that has that circle internal, and then the radical axis can be outside.
We can look at that. I haven't actually tried that one. So we're going to consider this case at some point, but this is the easier case for now. So let's look at this, because, I mean, how close can we get here? Because we know we can't have it on there, right? Because if it's on there, then the power of any point there is just 0, because it'll be the distance squared, which is be 0 squared, minus the radius squared, which will be 0 squared, because we know it can't be second. So that'll be 0, but the power with respect to this circle will be non-zero. So we can't have it on there. But can we get arbitrarily close, or is there some distance for which we can't do that? So let's try to work that out. So say we had some point that's like arbitrarily far away. I mean, I'm sure we can find one there because, I mean, it just makes sense. We can double this distance, like reflect it across, and then with the same radius, and then we'll have that radical axis. So we know there's some point here that's going to have this as that's going to have this satisfying. So we can remove this, and then we're just going to see how good we can get. So we have some point here which will satisfy that, and we're going to have a circle with unknown radius, and we want to work out the condition that this is true. So consider that point P on here. Now we know that if one point P satisfies that they have the same power, then all the points on this line are going to satisfy the same power. So we just consider the power of one point. And the power vector of this circle is going to be, I guess I should give these names. So let's call it O1. Let's call this 2. And then I guess we should give this a radius. Let's call this radius R, and let's call this radius small r. Now, the information we have is we know where O1 is, we know where R is, and we know what R is, and we know where L is. So we write down the conditions. Power of P is O1 P squared minus R squared. And we know that's going to be equal to O2 P squared minus R squared. Now, we need to find the locus of O2. So we want conditions on O2. But we also know that R is slightly variable. However, we have a bound on R. Like, what's the trivial bound on R? Bigger than 0.
Correct.
Yeah. So that's the most important one. So let's have bring R to this side and bring everything here on this side, because we know what these are. These are fixed. Well, ish. So we have R squared is then equal to O2 P squared minus an O1 P squared, and then we're going to add an R squared. So we know this thing must be greater than 0, or greater than or equal to 0. And so then we must have that O2 P squared is greater than or equal to O1 P squared minus R squared. So that's our bound about O2 P squared. Now, this is equal to O2 P squared minus convenient radius 0 squared, which is O1 P squared minus R squared. And now I think we have to go about trying to construct this, because I think that's what people want when you want to look at this. So let's look at what O1 P squared minus R squared is equal to, because that is equal to, we can factorize this as an O1 P minus R and O1 P plus R. And why not, just since it holds for all of them on the line, make it specifically the one that is between the two centers? We'll call this P. And that means that O1P minus R is going to be equal to, I guess we should give this point, let's call this point X, and this point Y, is XP.
What is O squared? Did you
O squared?
Yes, just the second last line.
Oh, that's 0 squared.
0. Oh.
0 squared. Yeah, because we can subtract 0 from this, keeps it the same. So O1P minus R, we just remove this side and we get XP. And then O1P plus R, is we get PY. And we get the familiar power of a point. And so we have our limiting condition is O2P squared is equal to XP times PY, where R is equal to 0. And we know that using power of a point. And, well, I don't know really what the specific one in this case is called. We can draw the tangent there. It's t. And then we know that tp squared. Okay, all right, down here. tp squared is equal to xp times py. Which means that TP is our limiting case. So that's how we construct our smallest difference, which means that the furthest we can go this way is when O2, I guess I'm just going to call this O2 prime, is when this equals this. And then if we go further that way, we can always select an R such that this is true. Is that clear? Is there anyone that doesn't understand that, please? Because this might be quite complex.
Why did you have to do the -0 squared?
That is just to show that this is some sort of power of a point. So if as we get closer, our radius is going to get smaller. We can't go smaller than a 0 radius. So we want to look at when this. It's an idea to sort of make sure that we're comparing the same sort of thing. So this is the power of a point. We want this thing to also be some power of a point, not just some square of some distance. Does that make sense? Sort of, it's just more of like an intuitive thing. So we go, this is some power of a point, this is some power of a point where the radius is 0. That's kind of like a tangent. And then so we think of the tangent. And that's how we realize that we can construct O2P like that. Cool? Is everyone good with that? So, and is everyone clear that if we go further than that way, then we're going to have, so if we go further than that way, so we have O2P squared is greater than this, which is equal to TP squared. Okay, then we're going to have that R squared is going to be greater than 0, which means that R is, we can actually do this thing. Makes sense? Great. So we know part of our locus, and now we want to handle the other case of inside here, which I haven't actually tried yet, and I have no idea if it's going to work. So let's see what happens. Right. So we have a circle. I think we have a few cases to try. So first, I guess we should try when the circle is centered on the side. So this is going to be 2, 1, it's going to be P, right angle. And so we have the power of P with respect to O1 with radius R, I guess R, is going to be small radius R. O1 P squared minus R squared, and we want that thing to be equal to O2 P squared minus small r squared. Now, I guess we do the same thing because we've got this down on R. R squared is equal to O2 P squared minus O1 P squared plus R squared. And we need this thing is greater than or equal to 0. So that means we require O2 P squared is greater than or equal to O1 P squared plus R squared. Sorry, that's not right, minus R squared, which is then equal to, as we did before, TP squared, where TP is the tangent. Right? So then we need that O2P is greater than or equal to TP. So I guess that means what we need to do is we need to draw this radius in there. So this is a circle centered at P, radius TP. point. So then we must have that O2 must lie on this side. So specifically, and I think it's probably fine here as well. Because, what do we do for the case when it lies on O1? Or do we just say exclude that case? Because then it would have the same radius. And I think if you go further, then you might run into...
If it's to the left, the radical axis will also be to the left. But if it's
Yeah, that's an interesting point. Like, are there two radical axes? Perhaps? If it's inside? Because we know this distance exists, which means we can have circles in there. But yeah, I feel that if we have a circle here. Oh yeah, but if the circle's here, we're presumably going to have a radius that's big enough to encapsulate the center, I think. But we can check that. So if it's on, well, let's just see how big these circles actually get. So if we are having O2p is greater than TP, which means it's on that side, and then we want the radius, which is equal to O2p squared O1, and we're going to have this thing is going to be equal to TP squared plus some small number. Actually, we need to know exactly what that is. Okay, well, let's just take a look. So, R squared is equal to O2p squared minus this thing. If we put it in brackets, that's just TP squared. And so, that's always going to exist. And as we get closer to, yeah, so the best way to do this. I don't think I'm ever going to get a right angle triangle from that. So what we're going to have eventually is, why don't we get a right angle? That's weird. Oh no, we do at some point. If we draw this tangent here. There we go. Okay. So the radius is simply going to be the circle where it passes through the radius. Yeah. Okay. Now I'm probably going to have to explain where I got that from. So if we consider the point here, such that we can draw a line that passes through our point O2, that is tangent to the circle, which we can always do since O2 is outside the circle. We know that, let's call this point, say, X, no, I can't call it X. Someone give me a name for a point. M, or N, M, whatever. Right, so that's going to be 90 degrees because that's a tangent, and that is going to be a radius because P is the center. And we know that MP is a radius, so it is equal to TP, which means that we have Pythagoras in O1 in our point O2 here, P and M, because that's a right angle triangle, which means R is equal to O2p squared minus MP squared. So our circle is just going to pass through that point. But I fail to see why we can't have circles on the other side. I feel like will it not work?
I mean, inside the circle.
If we have it going this way, but the radius just keeps getting really big.
Oh.
Yeah. You know what I mean? I think if we get past this side, then
Yeah, the circle's bigger than the other circle.
yeah. However, it can't get too big because then we're going to run into this. So let's take a look at what's on the other side. We're going to have exactly the same equations. And
Wait, Andrew.
yeah.
Does it matter if the new circle intersects that line? Because it just says in the construction.
Well, I mean, if the new circle intersects that line, we know that the power of the points in the line are going to be negative, and then some of the power is going to be positive, which means they're not. And for this side, we know they're all positive. So that we know that in our minds that can't be the case. So there must be some limit on how big this can get, based on some condition we're going to get here if we go further this way. So if it's on the other side, then we have the same condition, but we know that O2p squared is bigger than O1p squared, which means this is always going to be strictly positive, and this is going to be strictly positive. So we know we won't have any condition here, so it should always be fine. But how big does this radius get? It still becomes O2p squared minus TP squared. But how big is this? Because if it, say, gets really close to the edge, yeah, let's just say it gets like super close to the edge there, and that. Can we actually just, so where would that tangent actually be? It has to be 90 degrees with a point in the center, so I mean it should always exist. So I guess we should bound this R by saying R is going to be less than O2, R squared is less than O2p squared, which it is by definition. So we know it's never going to intersect that line, so that's fine. So we can get as close as we want to there. And specifically when it is there exactly, I guess let's just calculate what R is. So R squared is then equal to O2p squared, which is going to be O1p squared, or O1p plus R squared minus TP squared. What was just that angle? I mean, it's still the same. This isn't probably not going to give us anything interesting. O1p squared plus R squared plus 2O1p minus TP squared. Oh, well, we know what TP squared is. That's O1p squared plus an R squared. So we get that one cancels and the R1 doubles up. That equals 2 times R squared plus O1p. Oh, sorry. There's an R there. We'll take out the R. Yeah, okay. So then yeah, I think that's as far as we can actually take the problem. So we've shown that if we have a point. Actually, no, that can't be right because then it will intersect, won't it? Because if we get here and the radius is really big and it goes outside the circle, then at some point, since everything was inside the circle, it would intersect. So we have another boundary condition which is stronger than this one, which is we must have that R squared is less than. We need to take the distance between O2 P and this one. So is less than O2p minus O1p. That's going to be positive, and it's going to be this distance here, so I guess I should just put it here somewhere. So O2p minus O1p is going to be this distance, and we want this distance, which is r minus that. So we will take this. Yeah, O2p minus 1. Okay, so is that clear where I got that from? Cool. So that's our new bound, which means that we can get a limit on O2p by saying that O2p is less than or equal to r plus, oh, hang on, this is supposed to be a square. But I guess we don't really need the square, we can drop all those squares. So we have O2p is less than r plus O1p minus O2p. Sorry, we did minus r. But we know what O2p is from, what r is by construction. Oh, so maybe we do want to square it. Or do we just want to not do that? So let's just write this as, you know, O1 minus the square root of O2p squared minus t. Great. Right. Now, we know what the, well, we need more of this out, so we should actually keep everything squared. So let's do everything squared. Now we're going to get into messy algebra. Oh, actually, I just realized I'm just being dumb. So, let me just explain now. Okay, so bold claim, nothing here works. The reason why that is true is because we know that as we move O2 to the left, we know that R is increasing because TP squared is fixed, and this is O2p squared is getting bigger, which means R squared is increasing. We know that when O2 is coincident with O1, we must have that R squared equals O1p squared minus TP squared, which is equal to the radius squared from, if I draw O1 to T, that's not going to work, is it? Is it going to work? Feel like it work. What is O1p squared minus TP? Yeah, hang on, yes. So O1p squared minus R squared is equal to TP squared by definition, right? Which means swapping R squared and TP squared gives R squared. Which means small r is going to be equal to big R, which means if O2 is coincident with O1, we're going to have small r is big R, which means the circles are going to be exactly the same. And when they're exactly the same, the radical axis is, well, everywhere. So I guess that case doesn't really count. And if it goes this way, we know R is going to get bigger, which means that the circle is going to be, at some point, intersecting, I think. There's only one thing I would need to check for that. But I'm not sure. I guess I should do the check. And the check is to make sure that, in fact it would, wouldn't it? Because it would just grow it bigger. So it would still be outside. So this is rubbish, which means this is fine. I guess this is rubbish. So I guess then we were done, weren't we? Right, I'm okay with saying that's done. So, recap quickly. We have a circle, we have a line. We want the ones that are radical axes. Can't be here because then we have the radius is less than 0. Can be anywhere there, including that point when the radius is 0. That's all fine. Cool. Then here it can't be because then the radical axis is going to be there. If you do the math, I'm sure you'll come up with the same thing. Can't be here, same reason. Actually, no, it probably could be here because the radius can be really big. Yeah, but it can't be here with small circle, but it can be here with really big circle. And specifically, we're going to have the radius is defined by this, which we know is going to be strictly smaller than the distance, right? Because we can always, or will it? No, there might be a point at which it stops. Do we think there's going to be a point at which it stops or not? What's the consensus? There's going to be a point at which it stops? Hands up. Point that doesn't stop, never stops, goes on to infinity, hands up. So you've got one hand up, so I guess that's the thing. And we're going to find out by just looking at, since this is the radius, we just need to make sure that this thing is less than, yeah, actually no, it doesn't stop because, yeah, that's fixed. Yeah, cool, doesn't stop. Yeah, so it can be anywhere this way. Cool, there. So it can be anywhere that isn't here. Or 01. Right, and I think I'm probably out of time right now. Yes, I'm out. Yes.
So not technically be 01 since everywhere will be the radical axis, so O will still be part of the radical axis.
Well, I mean, if they coincide, there is no radical axis per se, so I just don't like it. Yeah. I mean, I'm sure coordinators would probably be okay with you saying 01 or 101. There might be something in there, I don't know. But, yeah. It's quite an interesting problem, actually. Yeah.